Good morning. I hope you're doing well. I'm doing very well. I think yeah. I was very caught up with some other things last week, so I wasn't actually able to get really any Juggleboard stuff done, which was a bit of a bummer, but it's come back around, and now this week I was able to spend a decent amount of time working through the Ball Butler development, let's call it. And yeah, it's come along nicely, and I'm very keen to share with you everything that I've done. So the first thing that I want to get to this week is some feedback from last stream, which was 2 weeks ago. And there's one thing in particular that took me a little while to understand, but I now appreciate that the person who suggested this is absolutely correct. And the crux of the problem here is that it's a bit noisy, with the pitch axis that we're developing for Ball Butler, so this one that comes up and down on here, this is like it's very smooth, it's very clean, it's very nice. I haven't actually operated this any more than what I showed a couple of weeks ago, where I was just getting it to like lightly, slowly move up and down. But from what I've seen, everything is very smooth, it's very controllable and everything. However, if you pay really close attention to it, what is supposed to be happening here is that we have this little spool that the motor is attached to, and that has the string wrapped around it. And then there's the bigger spool, the big red ring that the string then wraps around. And the idea is that as the motor spins, it wraps the string around the small spool, unwrapping it from the big spool. And for this to work like perfectly, the way that it's supposed to work, the string should be perfectly perpendicular to the axis of the small spool. If the string is not, if you imagine the extreme case where the string is off on like some crazy steep angle, then the amount of roll that the amount of like string that would need to be wrapped around the spool for the spool to travel like the correct amount of distance I find it very hard to describe this, and honestly, like, it's very hard to visualize in my it's a very, very difficult concept for me to describe. But basically, we want the string that is wrapping around the big red ring to be perfectly perpendicular to the small spool. Hopefully that is sensible. Now, of course, it's not perfectly perpendicular, because if it was, then the string would just be trying to wrap up in the exact same spot every single time. We actually want the string to be wrapping up and down the spool. For some reason, some of my motor phase wires seem to be touching every now and then. I don't really know what's going on with that. But yes, so it's not quite lined up. The string is on a very, very, very slight angle. And when the viewer, Mikkel, who I'll get to his pronunciation later, when this viewer first mentioned this, I thought, like, I don't see how this can be a problem, because like this is just purely by chance that this is the case. But in this exact setup that I have here, it seems like the angle that the string is at is pretty much the perfect angle to have this string wrap and unwrap along the length of the spool so that it's not trying to double over itself. So I was thinking, like, well, this angle A is extremely small, like it'll be like less than 5 degrees easily, and B is kind of seeming to work in our favor insofar as it allows the string to wrap around the spool. So I'm like, maybe this isn't a problem. However, I also remembered that in Ayed Musa's video where he makes these capstan drives, this is the one that I derived a lot of inspiration from for this design. He mentions that he had a really hard time trying to calculate the reduction ratio of this design, because this is ultimately, like, this is basically the same thing as having gears, and it's basically a gear reduction. And he had a really hard time trying to calculate what the reduction ratio would be and getting it to match up with experiment. Like, calculating it in theory is like, okay, cool, what's the diameter of this string spool? What's the diameter of the big red spool? Divide them together and you have your reduction ratio, in theory. But he was getting his experimental value, which he found by just like moving it around and taking the O-drive readings. That was always ever so slightly off of what his theoretical value was. And I'm kind of wondering if this is why. So if you're relying on like open loop control where you don't have any output, like encoder feedback of the actual angle of the whole thing, then it might be quite difficult to position this to get the exact right angle. Now for me, thankfully, I do have an output encoder on here, so I'm not terribly worried about this phenomenon at all, because even if the reduction ratio is slightly off of what I want it to be, I'm ultimately going to be commanding the angle of the arm, and the motor's just going to go to wherever it needs to go to make that happen. So I don't really care too much about the reduction ratio and all that in this case, but it's a very interesting thing. And he suggested a very interesting solution, which I have implemented in a branch of this, and I'm keen to show you. But I want to look at comments first. So Alice says, good morning. Good morning. Prop Guru, good day, friend. V-Groove. Prop Guru says, ooh, looking into sewing machines and how they rethread a bobbin. What type of string are you using? I'm using Dyneema. Let me get the spool. I'm using this stuff. 100% ultra high molecular weight polyethylene. You can get it on Amazon. And it's got a 0.8 millimeter diameter and 31 meter long spool. Yeah, it's quite good. It's super strong. And yeah, I have no complaints about it at all, except for the fact that tying these little Brummel splices to get the nice clean loop is so difficult. Getting that loop in there, that's an exercise in tedium. But other than that, I love these strings. I love how thin they are, how strong they are. Yeah, no issues at all. I've actually tried, so one of the hypotheses of Mikhail's idea is that the string would want to travel along the side of the red spool here. And also like the length would be changing as you're moving the thing up and down. And I've looked very, very closely. I had the thing right down the bottom, staring at the string at the top, and watching as I move this up, and the string doesn't seem to want to move. At least it doesn't want to move enough to actually make it move. Maybe there's just too much friction between the string and the plastic. I don't know, but it's a very strange problem. It kind of like breaks my brain a little bit. But I do have a potential, I've implemented Mikhail's suggestion for how this could be solved. So you may remember that, and just from looking at this, that the way that I have this set up right now is that the string is just coming out, on either end, it's just coming out of a little hole in the top. And to be honest, I'm not actually super happy with this anyway, because the hole is not quite, like it's sending the string in the wrong direction. So if I bring this right up to the top, hopefully you can see, once the camera focuses, come on. The string is not quite coming out at the right angle. It's trying to like go out that way, but we really want it to go out more that way. So I'm not super happy with this in the first place, but Mikhail's suggestion was to replace that hole with a slot. And I initially figured like, yeah, a slot, I like that idea because this would allow the string to move laterally. But of course we need to have some way to make that really low friction, because otherwise it's just not going to move. And there's no way that having the string just on plastic, that's not going to slide along, especially because this part is being printed this way up. So all of the layer lines are along here and the string's not going to want to bump along the layer lines. So after a little bit of thinking, I realized that this is a very good opportunity to use some of my new dowel pins. And I figured I'd use the largest one that I've got, which is an M8 dowel pin. And in principle, this should, I've tried like running, like I had the string over the dowel pin really tight and I tried sliding it along and it's fairly low friction. I could also put some like lithium grease or something along there to make it even lower friction, so it would slide along super easily. This dowel pin as well is slightly raised over the printed profile. I could, of course, raise it up just a little bit more, but I want to keep it as tangential to this surface as possible. And yeah, so hopefully you can kind of get the idea that the string comes along, wraps over this, it goes along this, it then goes around the ratchet spool, which is not currently in here. And yeah, in theory, this should allow the string to slide along. Now, I do realize that this kind of just shifts the problem down the line a little bit, where now if the string can slide along this dowel pin smoothly, that means that the angle between where the string is touching the dowel pin and where the string is wrapped around the spool down here is going to change. So that angle is going to deviate a bit, which is going to change that length, which is then going to change the tension in the string. So I don't know if this is really going to solve the problem at all, but I'm very curious to give it a try. And one thing that you may notice as well is that because of the tight bend radius that this dowel pin requires, because it's only 8mm diameter, I've had to swap around the direction of the ratchet, which thankfully, because of the way that I've modeled this, was actually not too hard. I just had to change like one feature and then flip it around. So now if we actually go into the assembly, I haven't bothered changing anything else in this branch of the model. No, you're getting spoilers. You're in the wrong one. What is this? In the main model, the ratchets are the wrong way around because I've had to change them. But yeah, thankfully, I have mirrored versions of the models of the ratchets and everything, so yeah, that shouldn't be too hard. And I'm very curious to know if this would actually help or not. Yeah, I don't know. I'm open to hear your thoughts. And yes, I agree, Alice and Prop Guru. The sewing machines are very, very cool. They are kind of magical, I think. The fact, yeah, they're just so good. They are so, so good. Definitely one of humanity's top inventions. Anyway. Yeah, so big thank you to Mikhail Hojbak? I'm going to go Hojbak for suggesting this. It took me, you can go back in the last live stream, this is where the discussion of this was went on, so you can go back and have a read through that if you want to. And it took me a little while to kind of understand what he was suggesting. And even now, it's still kind of like wrecks my brain a little bit, but I do think you're onto something, and I'm very curious to know if this slot idea will actually help or not. And I'm very curious if anyone's got any ideas of how to actually measure what effect this has and how to actually see if this is even a problem, because I'm kind of not sure how to test that. But in any event, very interesting idea. Okay, so before we head on to the main developments that I've got for this stream, I want to talk about something that we checked out in the last stream, which was how precisely I can position these motors. Because particularly for the base motor, the one that will be allowing this to rotate in like side to side, I was considering maybe I can just make my life a lot simpler and just have the motor directly attached to that output, and then the motor directly can turn this thing around. And I figured out before that I need to be within 1 degree of precision, which is a fairly wide margin. So that should be achievable, but I was just curious, like how precisely can I actually position these motors with the current ways of controlling them that I have right now? I am certain that there will be more sophisticated ways to control these motors that will allow for more precise control, but I'm just going to take what I currently am able to do as a given and not assume anything else, and then just move ahead with what I can currently do. So with that in mind, we did some testing, and I used this guy here, and we had this move around, and we could see on these little indicator marks how precise the motor was. And we were hypothesizing that maybe if we can initially the precision was was around a degree-ish, maybe like 1.5 degrees. It wasn't great. I was not comfortable to have the motor directly on the output. I was kind of wanting to go with some kind of reduction after what I saw 2 streams ago, or last stream 2 weeks ago. However, we kind of came to the conclusion that maybe the cogging torque, which is the fact that these motors kind of wanted to sit in certain positions, like it's really wanting to just click almost into certain positions. It's kind of hard to describe unless you can feel it. But because of that cogging torque, maybe that's what's causing the precision errors that we have. So I hooked this up to an ODrive Pro, which does allow for anti-cogging, and thankfully that process went by without any problems at all, which now allows me to control this motor extremely slowly and still fairly smoothly, much, much, much more smoothly than without anti-cogging on. However, that did not really help the position accuracy. And I have some videos here just quickly. let's just go straight to anticogging on. And actually, let's go zoomed in. Let's cut right to the chase because this is not the main focus of this week. So we've got anticogging on with the ODrive Pro. And so the idea here is that the large tick marks are 5 degree increments and the small tick marks are 1 degree increments. And this is recorded at 300 frames per second, which is why it's so slow. But if we skip ahead a bit, so what I'm getting this to do is to go in increments of 5 degrees and then stop there. So we can see like that one, that's pretty spot on. That's within half a degree, let's say. Moving up to the next one, pretty close as well, within half a degree. That one, not so good, almost a degree. There is potentially, that one's pretty close. There is potentially a little bit of parallax error in this as well, because I don't think that the motor was that the camera was perfectly perpendicular to this surface. So honestly, maybe that's what's causing some of these problems, but yeah, it's still around half a degree to a degree off. And then we zoom around. This will then wrap around back down to the bottom, all the way around. Still a little bit of overshoot. I need to do a bit more tuning. And yeah, this time around, like that's kind of far off. That's like that's like pretty much exactly 1 degree off. Pretty much exactly 1 degree. Yeah. So I don't know. I was kind of hoping that turning anticogging on would just fix this entirely and we would just go tuk, 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 straight away exactly to where we want to go to. But I think that I would need to have some kind of more sophisticated control to be able to get that level of precision. Yeah. Alice is saying, all I can think is the encoder has a big tolerance. I don't know. These are 12-bit encoders, so they should be pretty good. So these are the AS5047P encoders, which should be good. Kyle says, how do you measure the white lines for angles? That's definitely 100% accurate. Also good to see you, Kyle. That's a good question. I measured with my protractor. So yeah, it's possible that they are not quite right, especially because the protractor is kind of hard to do because like the center of where these all meet is like at the center of the motor, and my protractor is not quite big enough to reach to the markers there, so it's a little bit sketchy, but it looks pretty good. Yeah, it's possible that these are not quite at a degree, potentially. And Alice says, regarding the encoder, does the encoder see the error? That's a good question. I didn't actually check what the output from the encoder was on any of this. It's not a bad idea, but I'm not, to be honest, and also, yes, it is a magnetic encoder, and I don't know if you can get, I don't know if like the quality of magnets is really a thing. These are the magnets that came with the encoder, so I feel pretty good about them. Anyway, yeah, so at the end of the day, I'm kind of inclined to have some kind of gear reduction on the output of this axis anyway. It will be helpful to be able to shift the motor away from that central hole, just because that will allow me to put cables and stuff through there if I need to, or when I need to. And I feel like adding a gear reduction there is not terribly bad. So the fact that this is not quite getting the position accuracy that I want, I'm like, I could probably go really hard optimizing this and get this to work with just the motor directly as the output. But adding some simple reduction stage shouldn't be too much effort at all. And I'm not too concerned about doing that. Kyle says, I've started doing some small Arduino projects and have a gained a significant amount of respect for this project. It's harder than it looks. Yes. It's a lot. It's a lot of frustration, definitely. Yep. That's cool. I'm glad that you're starting on some projects. Anything cool coming up? All right. So let's go on a CAD tour. Let me show you what I've been up to. Also, I apologize for my sniffly nose. It is currently 12 degrees in my house, so I am a little bit chilly. Let's have a look. All right, so this is the updated. So for people following, like learning Onshape and everything, when I wanted to, because I wanted to test out this idea of using the dowel pin in here without affecting my main development, I actually made this as a branch in Onshape. So I now have this little branch over here. So, and I made sure, this is an important thing when you're using branches, make sure that you only change what you want to change in that branch. There have been a couple times in my use of Onshape where I have made a branch for something and then have accidentally started using that branch for other things, and then merging that into your main one just becomes an absolute nightmare. But if you make sure that your branch only changes what it's supposed to change, like in this case, I have literally only changed this one part to put the dowel pin in here. This is why I didn't change the ratchet pins. And that means that if I do decide to use this dowel pin idea, I can very easily merge this branch into my main branch, and it will just change that one thing and everything else will stay the same. So it's very easy to do. But yeah, for now, let's have a look at the current design. So actually, there's one, I want to show you one thing first. Yes, this is in here. So this is what I was thinking of having for the base. So I've had in the last 2 weeks, I've had some fun things arrive. One of the things is that I realized that I actually didn't have a linear slider that's the length that I need for this. So thankfully that has arrived. I've also got the M8 shaft that I'll be using for the pitch axis, and this has got nice threads on the end, so it should be very solid. There's no way this is going to bend, so I have a lot of faith that this mechanism is going to be a lot more stable once I change this over. And a very fun one that has arrived is the big ass bearing, as I've been calling it. And this is it's very interesting. It's definitely not as smooth as normal bearings that I'm used to. Like, I don't know if this sound will come up. I don't know if you can hear that, but it doesn't sound great. It's a little bit crunchy, but it's fairly smooth, and it's also huge. So yeah, I'm planning on using this as the main kind of like thing that allows the rotation of this upper stage. So let's have a look at the CAD. So this bearing is this guy in here, and this will spin around. And I want to show you first my initial plan for how to set up this gear reduction stage, and I want to see if you can notice any problems with it, because it took me a little bit too long to notice. So my plan was to have things set up like this. And what's the best way to show this? Let's do a section view. All right. Yeah, so my plan was to have the motor would be attached to the ground, and that'll be fixed. Also, the outer race of this bearing would be fixed as well, so that's not moving. But then the inner race will move, and I was kind of debating whether to use the inner race or the outer race to mount the actual, like, the top stage, and I ended up deciding on the inner race because it seems like if there are any lateral forces, which there will be when Ball Butler throws on an angle, it's going to be pushing to the side, albeit not by very much. But if there are any of those lateral forces, it seems like using the inner race is better, because then it's kind of like it feels like it's going to be pushing on more bearing wheels than if it were the outer race pushing to the side. I don't know if that's quite right, but that seems correct to me, and I don't really have any reason to choose the outer race, but I don't know. Curious if you have any thoughts on that. But yeah, so the outer race is fixed and the inner race is not. And what I'm about to do is to show you how I've mated this originally, and this mating is what caused me to go down the wrong rabbit hole. So I had this mated like this, and I was like, cool, okay, all of this can move. Obviously the motor's not going to move, but I'm too lazy to fix my mating, and I don't want to change it because I want to just keep developing some more of the other parts. And I didn't want to muck around with the mating just yet. So I figured, okay, cool, like the motor's going to stay where it is, but this all rotates the way that it should. Now this middle section in here, we have the three colors. We've got the black part, the red part, and then this black part in the middle. This will all be one piece, and it was originally going to be printed as one piece, but I quickly realized that both the red part and the smaller black part have aspects of them that are fairly tolerance dependent. And I think that printing these as separate parts will mean that I won't need to reprint the whole thing if there are any problems with any of these individual parts. So this big outer ring, I'll probably print with a big fat nozzle, so it'll be nice and quick. And the only really, the only aspect of that really cares about tolerance is this lip in here that interacts with the inner race of the big ass bearing. And that's a pretty relaxed tolerance, to be honest. So that's not too big of an issue. This smaller black one has the teeth on it, and that is has the belt teeth on it, and that is fairly sensitive to tolerance. So it's possible that that will need to be reprinted at some point. And so yeah, I basically just split this up into 3 components, and then they're all going to be fastened together with some probably M3. Yeah, nope, M4. All right. Some bolts to hold them all together, and that way it'll effectively be one unit at the end. Now, yes, so my plan for the belt drive was to have the output of the, so we're gearing this down, so we want the output of the motor to be smaller than the output of the, than like the end result output. And I haven't used belts before, you've got to keep this in mind, so don't judge me too hard. And I am still under the impression that belt tension is a very important aspect to using belt drives. This component is going to see fairly low torques, so it's pretty unlikely. I'm not too concerned about the belt skipping, but it's going to need to be tensioned correctly, at least at the start, and then it should be fine to keep going forever after that. But to get that belt tension correct, I'm expecting to not work immediately straight out of the box, especially because of something that I'll mention a little bit later. Yeah, so my original plan was to use these idler pulleys in here to help set this tension. And this is one of the things that I was expecting to want or need to reprint. So I have set up my belt document to reference the position of the motor and the output shaft, and I have originally drawn it in with no idlers in here. So it's just a straight smooth belt like this. I then have a composite curve and a measurement to tell me how long that approximate belt is. So here we see it's around 240 millimeters long. That's perimeter. And then I would use the idlers in here to help tension that belt. And my thinking was that, okay, if this position of the idlers is not quite right, then I can very simply reprint this red part, moving these holes ever so slightly to where they need to be to then get the correct tension. And I spent a little while trying to figure out a good way to do this so that it was adjustable, but I figured that if I only need to reprint this single red piece, that's like less than $1 of filament and probably like half an hour of printing time tops. So it's not really worth stuffing around so much getting it to be adjustable now when I can just try it a couple times and then get it right. So yeah, I ended up giving up on the adjustableness of it and settled on this. But there's a big problem with this. And actually, hang on, before I get to the big problem, to support the other end of the motor, oops, that's all one piece, to support the other end of the motor, because I don't want to be like torquing the motor over to the side while it's doing this, I have the output of the motor is this, at the very tip of it is this bearing, and that bearing runs along the outside of this red part. So that way, as the whole thing spins around, the bearing will push against this, and that will kind of support the motor and keep it vertical rather than it trying to be pulled in by the belt. And I was pretty happy with this. I was like, yeah, this is a good design. This will allow me to tension the belt in fairly in different ways, and like it shouldn't be too hard to get these idlers in here to tension it up. I mean, maybe it would be once the motor's there. Yeah, that probably would be actually. But I was kind of happy with this until I had finished this, and I was like, okay, cool. Now it's time to fix my mating. Now it's time to keep the motor where it's supposed to be. And that's when I realized that if the motor is not moving, then this whole thing doesn't work because the idlers are fixed to the moving part. And if the motor's not moving, then the idlers can't move either. And I was like, ah, crap. That doesn't work. Yeah. So that was a bit of a facepalm moment when I realized that. So it's no good. And I have now... I was about to say I've now learned this, but I don't know if I've fully learned this yet. I'm now more aware of the importance of setting up your mates correctly before going too hard into your modeling. Yes, because that is a stupid mistake to make. The motor shouldn't move, so the motor shouldn't move. Yep. so that was fun. So now let's look at what I'm actually doing. New design. Basically the same, except I've gotten rid of the idlers. Haha, solve the problem by just getting rid of them. And my thinking now is that to tension the belt, I will make the belt as close to as close to the exact length as I need to, as close to the length that it needs to be as I possibly can, and then just try it. And if it needs to be a bit bigger, reprint this. If the tension needs to be a bit more, then I'll reprint this red part with this surface that's highlighted being a little bit bigger or smaller, depending on which way it needs to go. And I'm aware that this is going to be a little bit fiddly to put together because, oops, let's bring the motor. Come on, I don't want the box. Let's just get rid of you. There we go. Yeah, I'm aware this is probably going to be a little bit fiddly to put together, and honestly the fact that the idlers aren't there is actually going to be easier to put together probably, because I'm not going to have to like screw through the motor, which I didn't even realize until just now. But I think it should be doable, because if I like rock the motor over on, then that should go on okay, I think. But yeah, I'm not super happy with that, and I think that we'll see how the tensioning goes. Yeah, this is the end result. And one other aspect of this that I'm a little bit concerned about is that I was talking with ChatGPT about this, trying to see how big of a gear reduction I can get. And actually on this right now, I've been using a lot of variable studios in this. Also, by the way, the link for these documents is in the description to this video. So if you want to check it out and kind of follow along, then you can. But yeah, so the big pulley has 90 teeth and the small pulley on the motor has 16 teeth, giving us a reduction ratio of 5.625 to 1. But because both of these are printed parts, that's very easy to change. Yeah, I found there's a feature script thing that someone wrote to make these pulleys, and it works really nicely. It's very easy to print these pulleys, or to design these pulleys with that feature script. So if you're curious to see that, then have a look at the link for these documents. But yes, so I was talking with ChatGPT about like what the maximum reduction ratio I can have on belt drives, because I don't have any experience with belt drives, and I was like, how big can I go? And the consensus seems to be around 10 to 1 or so. So yeah, I figured that as long as I'm beneath 10 to 1, it should be fine. And then once I had this all CAD'd up and I realized how the dimensions of things would fit, I thought, okay, this is probably about as big as I want to get, because I don't really want the motor to overhang the inner race here so that I can have a kind of box around it. So there needs to be a bit of a gap there. So this is probably the biggest reduction ratio that I can get to, probably. So how big is my belt? How big does my belt need to be? I asked ChatGPT and it said 200 millimeters estimated. I thought, oh, cool, that's great. I only have 2 looped belts, and those are exactly 200 millimeters perimeter. That's pretty serendipitous. How good is that? And I thought, oh, this is lovely. This is all coming together so nicely. I won't even have to worry about like stitching belts together, because my original plan was to have like just a length of belt that I cut and then somehow stitch up to be a continuous loop. But ChatGPT assures me 200 millimeters is the length that I want. So I was curious about if that was actually true. And I was also curious to see how well this sort of toothed pulley would print, because I have tried, even though I don't really have experience with belt drives, with a working belt drive, I have tried printing these pulleys before, and I haven't really had a lot of success. The teeth were not really finely resolved enough for the belt to get like a good amount of grip into them. So I wanted to just see how well I could print this now with my new printer. Especially, I recently got some 0.2 millimeter nozzles, and I wanted to see how well this would print. So I printed one off, and my God, 0.2 millimeter nozzle is so good. This part, when I showed my partner this part, she thought, oh, this feels light. And I thought, that's weird, because she's felt a lot of printed parts before. Like I'm no foreigner to printed parts. Well, this house is no foreigner to printed parts. I thought that's weird that she felt that this part of all of the other parts feels light. But we realized that because it looks so good, your brain kind of expects it to be heavier. Like it honestly looks like a proper industrially made part. There's one problem where when I tried to get it off the bed, I kind of mangled it a little bit, but it's so good. And better yet, it fits the belt like perfectly. You kind of have to pull a little bit of tension onto it, but I kind of feel like that's normal for a big belt. Oh, sorry, for a big pulley with many teeth. But once you do, let me just get this. Yeah, it is like perfectly meshed. Let me wrap this around a bit better. Yeah, have a look at that. Crisp. So nicely lined up. I thought, that's so good. The printing works perfectly. Let's see if my 200 tooth pulley, so let's see if my 200 tooth belt is the correct length. Bump bump. Not a chance. ChatGPT was way, way off. There's no way this belt is going to work for what I need it to. Which is kind of annoying because that means that we are back to needing to stitch together a belt. So I have a question for you all, which is, how do you stitch a belt into a continuous loop? I've done a little bit of research into this, and it seems like it is doable for bigger belts. I've seen quite a few videos of people doing different approaches. The one that I think is the most legit is, this is for a bigger belt, so keep this in mind, is the guy cut out like a tongue on the inside of, like imagine you cut out like a little slot on the middle of the belt, right in the middle, and then on the other end, you cut out the outside, so you have just that little narrow bit, and then you insert like the tongue into the gap of the other one. And then, to hold it together really, really solidly, he had them lined up and then drilled holes through the... I'm not even going to focus on this, it's too small. He drilled holes through the round parts of all of those overlapping teeth, and then inserted a screw into all of them. This is a much, much bigger belt than what I'm dealing with here. And that seems super solid, because that means that the only change that you're making, and I think he also added glue in there as well, the only change that you're making is within the length of each tooth, which means that the whole thing is going to roll perfectly after this attachment is done than what it would have been before. And I love that attachment. I've seen some other really sketchy ones, people using like staples to connect to them, and yeah, that sort of thing. And I obviously don't love that, because this needs to be able to roll around pretty much it. So I'm not going to be rotating this system by more than 360 degrees, but I'm just basically taking it as a given that the belt will need to be able to, like this cut point will need to be able to roll around these pulleys. So yes, whatever connection method we use needs to maintain the tooth profiles, and also needs to be strong enough to not just rip apart. Now, the most, I don't know, the approach that I have the most faith in right now is to cut the belt at an angle and then use super glue to fuse those two angles together. That seems pretty strong. But in the video that I saw of where the guy did that, he's like, yeah, this is so strong. Look, I'll show you with all my force trying to pull it apart. And then he pulls it apart. It's like, obviously didn't hold. And that's like right at the end of the video. Like he's like, whoo, this was a success. Like you broke it. Like it's not a success. So yeah, I don't have a whole lot of faith in that. I'm thinking that maybe if I do the super glue and I also add like thin strings along the back and like glue them on as well, just to add a bit of tension strength, maybe. But I don't want to mess around with with like the tooth side of things, because I need that to mesh really nicely with the pulleys. So that's potentially going to be a bit of a hassle, but we'll see how we go. I'm sure someone must have figured out a good way to join these. These are GT2 belts as well, by the way. Someone must have figured out a good way to join GT2 belts together, because people use these belts all the time. So I'm confident that there's a solution out there that I'm just not aware of. Yeah. Kyle asks what printer. I got a Bamboo H2D, and it is lovely. It is so good. I used to have the Prusa i3 Mark III's, and this one's a definitely big upgrade. Big upgrade. All right. Yes, so this current approach, I think, will work nicely. The main thing that I need to work on with this design right now is to figure out a way to attach the motor to essentially the outer race, so that I definitely fixed. Yeah, okay. Like, I swear that the motor should not be moving, because I fixed my mates in this version, and now we can see how this actually works. So the motor stays still, as it should, and then the inner race moves, and the motor is attached to the outer race, which should be fixed, but whatever. They're fixed relative to each other. Yeah, so I need to figure out a way to mount the motor, but I'm kind of, unsure about that, because the box that I have around the outside, I've only very, very loosely started on that, and I'm just trying to consider what other things I need to put in here. And there are a couple other questions that I have for the structure of the whole robot that will inform what else needs to go in this base box, and that will set how tall, how much space I need in here, and that might affect the motor mount. So I haven't gone to too much work to fix this motor down yet, but that's the next main thing for this stage of the robot. All right, so let's have a look at the whole thing now, because there are a couple other changes that I've made as well. One of them the most obvious one, is that the main ring now, I think, looks a lot sexier. It's got this nice big curve in it, which I love. And the reason why I have that is because I have swapped the position of the O drive that's controlling the hand motor onto the other side. And I believe John suggested this on either Zulip or the YouTube comments at some point. And I think it's a very neat idea. It keeps the whole thing much more compact. And you'll also notice that, well, part of the reason why this works is that I have swapped the O drive Pros for O drive Micros. And the reason for that is because these ones are just so much smaller, so much more compact. I don't already have them, but I've already bought them and they're on their way. So I'm not too, it was a little bit of an impulse thing, but I think that these will work very nicely I think that these are much more suited to the scale of this robot than the O drive Pros. The O drive Pros seem a little bit overkill, and yeah, they're also huge and they don't really fit super nicely with the rest of this. So because we're swapping to O drive Micros, this fits a lot better in here, and I think that looks real nice. And same thing down here, I've swapped this one to an O drive Micro. So yeah, so that will read the absolute position of the pitch arm, and then everything else, a lot of the other things have stayed the same. All right, so so one other question that I had is running something that I've been very, very mindful of, especially in the last week or so as I've been working on this development, is how to run cables up to the upper stage up here, which will need power and communication and everything. So this motor up here will probably have a commutation encoder, probably using we'll definitely have a commutation encoder, but we'll probably be using one like a custom PCB that I make, because I'm very keen to do that. So it'll basically be this green board with its attendant chips, except instead of on that green board, it will be on my, why can't I just show that one? It will be on my, I don't know how this decides what to show and hide. Instead of being on this green board, it'll be on this blue board here, and it'll be that shape. That encoder data will run down, and that will come down to this O drive Micro down here. So that doesn't really, like the only communication, the only cables that need to run up to that will go through this O drive down here. But this O drive over here will need to have power and CAN cables going to it. So that's going to need to run down through the base somehow, through this rotating section, which is not rotating right now for some reason, down into the base here. And I've put a fair bit of thought into this, and I'm not exactly sure what the best way to go is, but one possible solution that I had in mind was potentially using an off-axis encoder, because that would mean that we can hollow out this entire middle section and have the encoder off to the side somewhere, and then the cables can very easily run straight through the center. They will only ever be twisted rather than twisted and translated, which will be very nice. So I thought, this is cool. Maybe this will be a great opportunity to try playing around with an off-axis encoder. And I'm very open to ideas on this. If anyone knows of a way to do an off-axis encoder relatively cheaply, I would love to know. As far as I can tell, it is possible to use a magnetic encoder with the encoder off to the side. If you use a magnet, let me just quickly show you this. Hopefully, yes, nice. So this right now is a diametric magnet. It's got north on one side and south on the other. If we wanted to use this magnet as an off-axis magnet, then we can set it. Where are my ring magnets? Here. We can use a ring magnet with north-south split up in a different way. And I could not get my Onshape model to work properly to divide this into like multiple poles. So pretend that the coloring works and pretend that they're all equally spaced. It's not correct. And yeah, I ended up moving away from this, so I stopped trying to bother getting this correct. But the idea is that you have a ring magnet that's like this, where you have north-south, split up all the way around. And then you have the encoder off to the side, somewhere over here, and that detects those north-south changes. That seems like it's possible to do. I have two questions about it though. One is that where the fuck do you find a magnet like that? I found a grand total of one magnet that's like that, and it has a fixed number of poles, which they don't even tell you in the data sheet. Like, surely that's a pretty useful piece of information. But no, they just show you like they put the magnetic tape, this sort of stuff over the top, and I guess you can like count from that image how many poles there are, I guess, but surely that's pretty useful information for them to include. Apparently not. But I've only found one that's not like $300 for just the magnet. And yeah, also like it seems like it's kind of hard to set up the encoder to be positioned like that. I have found a couple pieces of software from the encoder manufacturers like AMS and like the TI, I think, yeah, Texas Instruments. Yeah, they both have like simulation softwares that you can use to kind of test out how well your encoder will perform with the magnet in different spots. But it doesn't seem very easy at all to get the magnetic encoder to work that way if you want to have absolute control and if you want to use any arbitrary magnet that you have yourself. It seems kind of annoying to do. So I was looking into other off-axis encoder options, and this one came up a bit. The AXIM, off-axis rotary absolute magnetic encoder. And I thought, damn, this thing looks so good. It's got 20 bits of resolution, which is absolutely nuts. My current ones are 12 and maybe 14. You can pick what kind of communication protocol you want to do. It's extremely thin, only 7mm thick. And I thought, oh, this is great. This is exactly what I want. And then I went through the process of configuring exactly what I need. I chose like the lowest spec version of everything. And the price for one of these came out to €408, which is definitely more than I wanted to spend on this component because I don't really need it at all. So yeah, I'm definitely not happy to spend whatever that is, 700 Australian dollars for just that. So yeah, as soon as I saw that, I thought, okay, no more off-axis encoder. That's not going to happen. So now I have gone, I don't know, back to, or just to, having an on-axis encoder down here. But I don't love this. I really don't, because passing, so I then have these cavities around the outside to pass the cables through, but I really don't like that. I can just see that if this ever does spin more than one revolution, then that's going to really cause problems with the cables getting tangled up. So I'm thinking that a good workaround, because of the fact that I probably have to have an on-axis encoder here, is to have some kind of mechanical stop that just prevents the thing from rotating more than 360 degrees. So potentially wherever the motor is attached, why is this not spinning? Potentially wherever the motor is attached, I might have like just like a printed raised section that the spinning part will just bump into, and that will just physically stop it from rotating more than 360 degrees. And that way the cables will have less likelihood of getting tangled up, I guess. But there's another problem, which is that like I don't really know how to if I put a normal encoder on there, like let's say that we grab, let's take this. If we put this down here, and let's just quickly mate it. Where'd you go? This is a problem with doing text the way that I have. It screws up the center point. There we go. And we want that to be spaced by 1.5 millimeters away so that we get good readings. If we have that there, that's really cutting off our space for the cables to come through. So yeah, I don't love this. I do want to have an absolute encoder on this output so that way we can see exactly what angle the whole thing is positioned at. I think that's going to be pretty important for getting accurate throws. But I don't love how much space this encoder takes up. I can't shake the idea of making a second custom encoder that is kind of more fitted to this situation, but I'm in two minds about that. Now, a big thing with this is that it might look like this is completely fine, and it's like, okay, cool, this encoder doesn't really block that much space. Like, there's still all this space up here for the cables to run through. That's not a problem, except for the fact that once this starts spinning, that's going to act like a little knife. It's just going to chop the cable. Like, I don't know why this isn't spinning. Why are you fixed? Let's make this revolute. I think this might be why. Nope. Okay. If you imagine this encoder must not spin in order to get the readings from the magnet. So if that's not spinning and this upper stage is spinning, which I don't know why it's not right now, then yeah, that's just going to chop the cable at that point. So yeah, it's a little bit tricky. Having an off-axis encoder would make this whole problem so much easier, but I don't know how to do that in a not extremely expensive way. Yeah. Any ideas are more than welcome. Okay. Now, I have had another thought, which is to do with the power here. So I don't want to have... I mentioned in the last stream that I don't want to use the hand motor to break the hand, like to slow it down, after the ball has been thrown. Because if we look at the hand in here, there's a couple of reasons why I don't want to use the motor to decelerate the hand. And to get an idea of exactly what I'm talking about, ball is in the hand comes up to, I don't know, let's say halfway along. It then needs to start slowing down so that it doesn't just ram into the end max speed and then wreck this little stopper thing here. So once it reaches the max speed, the ball will continue on its merry way, but then the hand needs to slow down some way, in some fashion. Currently on Jugglebot, the way that this is done is by using the hand motor itself. It just brakes and slows the hand down that way. And that's fine because for Jugglebot, we have quite a lot of stroke for the hand here. But for Ball Butler, on this one, we don't really have that much at all. And to be able to get decently high throws, we're going to need to use most of this stroke just for accelerating the hand to throw the ball in the first place. So we really want to minimize the amount of distance that we need to break over. And I want to try to minimize the amount of power that I'm sending back through the system. Part of the reason for that is because I only have one regen clamp that is kind of suitable for this purpose, and that's currently being used on Jugglebot. And Jugglebot kind of deserves it a bit more than Ball Butler does. It's also kind of large, and yeah, it would just take up more space. So I don't have or want to use a regen clamp here. I really don't want to be sending this power back along the 12-volt bus because that's going to go straight to the Jetson. And I'll talk about that more in a sec. I have a few things to say about that. So I got to thinking, and we were talking about this in the last couple streams about potentially using magnets or eddy current braking or various solutions along those lines. But I remembered back to my childhood when I used to make RC cars with my dad, and I remember him showing me the spring mass dampers that they have in these cars, and how they've got like the little They've got the disc in them that has the holes cut out in it, so that way the oil can go through. It's basically like a syringe, but instead of having a sealed face that slides in and out of the syringe, it's got holes cut into it with oil in there, and that way when you push, the oil can go through, but because the oil has some viscosity to it, it can't go through immediately, and so it takes a bit of time to work its way through that disc with the holes in it, so it stops you from just immediately compressing the whole thing. It acts as a damper. And in the case of the RC car shocks, they combine this with a spring and you get a spring damper, which is a very common thing in like mechanical systems. And yeah, I thought, I have a giant bag of syringes, which might sound a bit sketchy, until you remember way back to the original, it's probably my first YouTube video where I had the Stewart platform that was hydraulically actuated. And if you think I've been naive with some of my solutions now, you should go back and watch some of my older videos because, and I don't even know if I really mentioned a lot of these things, but I was expecting this whole project to be fairly straightforward. I thought, okay, cool, I'm going to use syringes to actuate the Stewart platform, and that's just going to work because why would it not? So let's just buy like 100 syringes. I don't even know how many there are, but let's buy like a shitload of syringes because I'm going to need them eventually. Once I build like 15 of these Stewart platforms, I'm going to need a lot of syringes. So let's buy lots so that we're ready. Needless to say, almost all of them are still in their original wrapping. I also bought like 15 stepper motors for the exact same reason, and same thing, most of them are still in their original packaging. But because I have all these syringes, I thought, maybe I can make my own damper systems with these syringes. And I was playing around with them and I thought, yeah, cool, like they're a good size, I could like chop them down. And I can 3D print some different plates to go on instead of the sealing element, and they can have the holes in them. And I can print this with different sized holes, and that way I can like tune the damper to be exactly the way that I want it to be. And I got so far as to plug the end of one of them with like, whatever it's called, the really strong glue, and it seals pretty nicely. And I thought, this is coming along really well. Until I realized that if you are making a damper and there's holes in the sealing part, so it doesn't actually seal because it's not supposed to seal, it's supposed to let the oil through, that means that there's going to be oil above the sealing element, which these syringes are not designed to do. That means that if you compress this and you have oil above and you tip it upside down, the oil's just going to, or if you just tip it upside down in the first place, the oil's just going to come straight out. So I don't think that's going to work very well. That was a bit of a stupid oversight. But the end result is that I basically just bought these. As soon as I realized that problem was a problem, I just thought, stuff it, let's just buy these, see how good they are, and probably I can take these apart, and then if I want more or less aggressive damping, I can just change the size of those plates in there and tune it myself that way. So we'll see how these go. These should be here, as it says, they should be here on Sunday, so fingers crossed they'll be here soon, and I'll be able to play around with those. And I quite like this idea, because these, I mean, they have no, they have, 3 inches on here. So I suspect these should be pretty small, and I should be able to like stick them around on the sides of this mechanism here to, slow this, to break this hand. And so I'm pretty keen on those shock absorbers, that kind of shock absorber idea. I'm very curious to know if people have concerns about that, because it feels a little bit too easy almost compared to like magnets and eddy current breaking. It feels, I don't know. We'll see how it goes, I guess. We'll see how stiff they are. But on the flip side of this, a big thing that I've been thinking about, especially when I was going through the process of thinking about transitioning from the ODrive Pros to the ODrive Micros, a big thought in my head is how much power is needed to A, throw the ball, and then B, decelerate the hand. And more importantly for me at the time when I was thinking about this is how much power do I need to throw the ball? And I ran the calculation for a throw height of 2 meters over a throw distance of 0.2 meters, which is this entire stroke. And I got the result of 30 watts. And I thought, cool, 30 watts isn't too bad. The ODrive Micro is rated for 100 watts, so that should be completely fine. And also my power supply is 12 volts, but it's 5 amps. So 30 watts by 12 volts is whatever that is, 2.5 amps. So my power supply should be able to handle that, no problems at all. But there's a big problem with that, which is that my assumption was that the throw distance was over the entire length of this hand, which it can't be because we need some distance to decelerate the hand at the end. And to cut a long story short, if I show you my my calculation, you can verify this yourself if you want. What's this doing? The end result has, let me get my pointer. The end result has the distance that you are throwing over on the denominator right here, which means that if, as that distance decreases, the amount of power that you need goes up at the same rate. And the end result is that if we use like half of the stroke of the hand, which I think is a pretty reasonable amount, like maybe we should probably be able to use a little bit more than half, but let's just say half, then our power needs go up to 60 watts. And if we have 60 watts at 12 volts, that is the full 5 amps. And that power supply is the power supply running the Jetson and the CAN bus, and it's going to Juggabot and Ball Butler. And if we take the full 5 amps just for this one throw, then that's just going to overload the power supply and everything's going to turn off. So I don't love that. But that is for a 2 meter high throw, and that's pretty high. So on the one hand, there is a hard limit on how far we will be able to get this to throw the ball because of the power supply. On the other hand, maybe we can get rid of this problem entirely and also simplify, for example, the cable routing to the... we can simplify a lot of problems if we remove this system entirely, and instead do what some people were suggesting a couple weeks ago by using springs to throw the ball instead. So we would have some, like a small, weak motor, or it could be any motor really, but it can be small and weak, to load up a spring. So we go loading it up, loading it up, loading it up. And then once we reach the point that we are at that we're happy to throw, then some trigger is released and it's thrown up. So let's say that there's like springs along the back here, along the spine, which I think would be a very elegant spot to put them. Then we can just have a motor just to pull it down. And then as soon as it's triggered to be released, the motor disengages and that launches up because of the springs on the back. I originally said that I wasn't too keen on this idea because I thought that would be harder to tune to get the throw heights to be correct. Because as it is right now with the hand motor, I feel very good that we can get it to throw exactly to the height that we want it to, especially after like a little bit of mucking around. Because I've already been doing that on Juggabot and that works very well. So I feel confident about that. And I feel a little bit less confident about the spring idea, because if we want to throw the ball using springs to varying heights, that means either we change the springs, which I don't want to have to do dynamically, unless there's some really clever way to do that, which I'm all ears. But in lieu of that, we would then have to, if we're using the same springs, we'd have to change how much we are pulling the strings down by before we release them, which makes it a little bit mechanically tricky, because we need to be able to, we need to have some mechanism for tensioning the springs and being able to release them at any point along that line so that the motor is completely disengaged, because I don't want to have to be I don't want to backdrive the motor at all. That's kind of the whole point of this, is that we would remove the motor entirely from the system when it's actually doing the throwing part. But I don't really know how that would work. I think that that is mechanically quite complicated, and I'm sure that there's a good solution for this, and I've only really been thinking about this for like the last less than 24 hours, so it's possible that I just haven't thought of the right thing yet. But yeah, if any of you have any ideas for how to engage a spring and hold its tension, hold it really tight, and that's probably going to be a fair bit of force in there, and then to be able to disengage, I'm happy for it to like go through a stage where it unloads the motor and then loads up like a pin or something instead before it throws, because this will not need to have like a crazy fast cycle time. I'm like one throw every like couple seconds will be absolutely fine. And yeah, so I'm happy to have like stages to this, But even allowing for that, I'm not too sure how to, like a ratchet kind of mechanism maybe that like clicks it along, but then how do you disengage that quickly without it interfering with the thing unspooling? Yeah, it's tricky. Yeah, and I'm very open to ideas. But if someone, so my thinking right now is that if no one, including myself, can come up with a good idea for how to do those springs, then I'm just going to stick with the hand motor as it is and just make sure that we're not throwing crazy high. Because I mean, if we do a 2 meter throw with it on the shelf there, it's going to be like through the roof. So yeah, it should be 2 meters is plenty. So this will be fine for now, but in the future, like especially when this is throwing to me, if this is on the ground and it's throwing to me, I mean, my hand is definitely not 2 meters high, but I may want it to be throwing that high so that I get a bit of an arc so that I can see the ball before I catch it. And it's not out of the question that it will need to throw that high eventually. So yeah, for now, I'm thinking of sticking with the hand motor just because I have it there and it's relatively straightforward in some ways, but in like cabling ways, it's a little bit more complicated. But I really like I'm now coming around to the simplicity and the elegance of using springs. And like having springs to throw and then like this kind of damper to dampen that motion feels very, I don't know, like industrial. It's very, very mechanical. And I'm a big fan of that. So yeah, any suggestions along those lines are more than welcome. Okay. Now, I want to talk about the power situation because this is something that I haven't really mentioned, and I had an awareness. I made a discovery on this that is not a very happy discovery, and I'm seeking better ways to do this. So here I have the Jugglebot computer, the Jetson, in its nice case. This is a new case because the original problem that I noticed was when I was going through the CAN bus stuff 2 weeks ago, trying to get the CAN bus sorted out with the ODrive 3.6s, I realized I was using the CAN, like the listener chip thing, the CAN to USB chip that I have on here. I was using that to read those CAN messages, and I realized that it's got a bit of like, I don't know, it was very dirty, very dusty because it was exposed. The old case that I had here did not cover up anything. It did not cover up that stuff. So this was just sitting there exposed to the elements right underneath my window, and which is often closed, but sometimes isn't. And I figured that it's probably not a good idea to leave that so exposed. So I decided I would remake the case and set it up to cover up this component at least, so that it didn't get covered in dust and wet and whatever else. In the process of taking this all apart, I made a very unhappy discovery, which is related to my power supply situation. So I have a 12 volt, 5 amp power supply off to the side. That comes into this jack, which is the jack of the Jetson. Like this is the Jetson here. And to run that power, to run that 12 volts out to the CAN bus and to what will be Ball Butler, I've done a bit of a dodgy. I have soldered onto the only exposed pins that I could find of that barrel jack. So the red one is right on the back and the black one is on the side there. And like I've given them a good tug, well, especially originally, like I gave them a good tug. I thought, yep, they're on there. I don't really love how dodgy it looks, but they're on there. And then I put it all away and everything was fine. But then when I went to replace this case, I realized that the black, at some point, it probably was when I was taking the old case off, probably. But at some point that black cable came off and was no longer attached, which is a problem because then it's just dangling around everywhere. And also like that means that I have no ground reference at all for either the Jetson or the 12 volt bus. Like nothing on here has ground. Actually, that's not true. Sorry, the Jetson would because the Jetson's still connected the way that it's supposed to be. But my CAN bus system and everything on the 12 volts has no ground. So I that was obviously a problem. I have obviously since soldered it back on, but I'm kind of wondering if this is even a legit way to do this. So I've made up, to make it a little bit easier to understand, I've drawn up a fairly rough wiring diagram here, which will hopefully let you see what's going on. So we've got a 12 volt 5 amp power supply. That power is coming out to the Jetson with black and red in the way that I just showed. And then that's going out to the Juggerbot O drives. The green and the yellow cables here are the CAN bus cables. And so of course, like right now, this is not here. Like all of this stuff doesn't exist. Why can't I highlight? Okay. But in the future, that will. And yeah, I guess my concern, my question here is like, if I did pull, let's say I pulled like 4 amps through this cable, which is going out to the 12-volt bus, which this will be powering Ball Butler. Will that affect the Jetson at all? Because they're connected to each other here, but like the Jetson's stuff is after that. Like in my mind, the power should just go, this is kind of hacky, but let's draw on this. In my mind, if I am pulling like 4 volts over here, that power will go through like this, right? It's just going to skip over the Jetson. But I'm very aware of the fact that I'm not, electronics is weird and I don't fully understand exactly what's going on with a lot of electronic stuff. So I'm thinking like maybe it's possible that some of that current, or like, I don't know, electrical inertia, I guess, will find its way into the Jetson and then somehow damage the Jetson parts. Because I really, really don't want to damage the Jetson. That's like top priority. Don't break the Jetson. And yeah, I'm open to suggestions on how I can do this power routing so that it's less likely to break the Jetson. Or if this is completely fine, if anyone knows or can offer some, I'm not going to blame anyone if anyone says that it's fine and ends up breaking. Of course, I'm the one ultimately making the decision. But if anyone actually knows if this is legit, I would very much like to know, because I don't feel super comfortable with it right now, especially because that cable came off before and it's like, well, what if it comes off again? Yeah, don't love it. But yeah, to finalize this wiring diagram, of course, in reality, the way that this is actually set up these cables are significantly longer out to Ball Butler and out to the Juggerbot O drives. So like the CAN bus will have the Jetson will be pretty much in the middle of the bus, and it will just go from the O drives out to the Jetson, out to Ball Butler. So Ball Butler and I guess the hand of Juggerbot will be the 2 ends of the CAN bus. And then same thing with the power lines. So the power will start here. Hopefully the high current stuff just bypasses the Jetson. The Jetson takes what it needs and then everything else goes to where it needs to go to. And yeah, the Jetson doesn't break is the plan. But yeah, very open to feedback on that, because it makes me a little bit uncomfortable. Okay. What else? Yep. Let's go back to the PowerPoint. I have another follow-up on my Onshape library suggestions. So over the last couple streams, I have made various suggestions on how to set up an Onshape library for like standard parts. And I believe I have finally figured out how to do this properly. And it's very nice. The end result is very, very nice. So much so that I'm potentially going to go back and change my fastener library to be the same way, but that's going to be a fair bit of work. So we'll see how we go. But I have a washer library because I needed to import some washers. And the link for this document is in the description if you want to check it out. So I'll show you the end result here is that we have a washer. Right now it's set to M5 washer. And look at this. The name of the part is M5 washer, which means that in any other document that I have here, that name will come up correctly, and actually I've changed this aspect of my fastener one. So now I can actually see what the fastener is, which this feels like a minor thing, but in the past it was just button head screw, button head screw, button head screw, even though they were like all different sizes, all different shapes and everything. It's very confusing to figure out. Like I would have to actually highlight on it and then read what the configuration was to see what that fastener actually is. But now it's in the name. And it's the same thing here. So if I change this configuration to be like M3, you have M3 washer. Very nice. And look at this, only one feature in here. Super nice. The way that I've set this up is like this. I have a tab for an arbitrary washer that allows us to set whatever inner diameter, whatever outer diameter, whatever thickness we want. And that will make our washer. And so this is using configuration variables, which you can make. If you go into the configuration thing, you can click down here, add configuration variable. And then when you make your sketch, you just reference that variable. So this is inner diameter and so on. So we have this arbitrary washer that we can make however we want. And of course we can import this as well. So if we have like one of a kind of some weird arbitrary, like some different washer that's a different shape to all the other ones that I own, I can still import that. Unfortunately, it will just come in as a washer. I don't know how to get the naming working for that, but you can still do that. But then for the generic components, the ones that I have a million copies of, what we do is we derive, so we go derived part, you select the arbitrary washer, and then you can set in the configuration what those variables are from the arbitrary washer. So the arbitrary washer has variables of outer, inner diameters and the thickness. And then in the generic washer, in these configurations, we can set what those variables are. And that means that when we change from the different sizes, their sizes will change respectively. Also, I don't know why my M4 washers are just really thick for some reason. I don't really know why. Just the ones that I have. Yeah, but then to get the naming to work, which is like the cherry on top of all of this, if you go into configured properties over here, you can add a property and add the name, and then in the configuration you can set the name. And you can of course make this whatever you want. So you can make the M5 one be like blah, and that way when you go to M5, its name will be blah. You can make it, yeah, whatever you want. But yeah, this means that when you import the parts, they come in and exactly like with the naming that you want them to have. You can change the color as well and everything like that. It's all super nice. I wish that there was a way to, and if anyone knows how to do this, then I would love to know. When you set this name, you can't seem to be able to reference any variables. So if I want to make this name like the outer diameter, that doesn't work. It just comes up as hash outer diameter. So I don't know if there's some like fancy syntax that this box requires to get that name to be right, but I would love if there's some way to, let's delete this. I would love if there was some way to set the name to be referenced off of variables. So that way, as you change these, like if I change this to be an 8mm inner diameter, that updates in the name as well. That'd be super nice. But I don't know of any way to do that yet. But yeah, definitely recommend doing that for your main parts libraries. All right, cool. I believe that is everything. I'm pretty sure. Yep. So I'm very happy with how this is coming along overall. It's looking nice. I can't shake the feeling that getting rid of the hand motor is going to really simplify the mechanics here. Well, the routing at least. I think that aspect will be made a lot simpler. I need to change this. I still need to fix how I'm doing the cable routing from this O drive down here up to the top of the motor. Oh, now it spins. All right, cool. Ah, that's not attached to that. All right, I got to fix my mates apparently. Yeah, but it's coming along nicely, and I'm considering having this ring be like inset into the base a little bit to kind of make it a little bit more compact. We'll see how we go. And if you want to see roughly what things will look like on the shelf, then this is it. Get rid of this. So I suspect that I'll be able to make the box underneath a little bit smaller than this, I hope. We'll see. Yeah, it's tricky there's a lot of different aspects of this that need to all work together for this to work the way that I want it to. It's like, do I use the main 12-volt power supply for this, or do I use batteries and then have like an isolated CAN transceiver to communicate? Maybe batteries is the way to go. If I have batteries, then using the hand for braking is going to be no problem at all, because I can just send that power straight back to the batteries. So that aspect would be nicer, but then I have to store the batteries somewhere. Yeah, there's lots of things to consider. But overall, I'm very happy with how it's coming along, and I really feel like this design is going to be pretty solid. I'm trying to be mindful of like scope creep. At the end of the day, I do want this to just be done and to work, and then to be able to get back to Jugglebot stuff. but I do want it to be good as well. So it's very tricky. It's very tricky, but we're getting there. And I feel pretty good that this will work and it will be very clean and very nice. Another big, the hopper is another big thing to get the ball back into the hand, but I feel like I'm more happy with like a janky solution for that, like a temporary solution for that. As long as like the rest of it works well, I'm pretty happy. As long as the ball can get into the hand, then I don't really mind if it looks a bit crap. But maybe I'll feel a bit differently when we get to the stage of actually designing that. Yeah. There's one other final thing that I'm going to bring up, which is an update to my electronics binder, which some of you might be interested in. Alice says, I'm literally right now having this problem with another project. Yeah, it's tricky. There's a lot of considerations that you have to make to get things to work nicely. But I've been trying to just focus on like the most important aspect at the time. I have been deviating a little bit. So like when I knew that I wanted to have some kind of belt drive for the base down here, similar to this, I was still spending a lot of time faffing around with I realized that I wanted to use a belt drive, and then very shortly afterwards I was like, oh, maybe I can use the O-Drive micros as well. Let me just see how they would look if they fit nicely in here. And I spent a fair bit of time designing an O-Drive micro enclosure sort of thing on this side, so that is where the O-Drive Pro used to be. And I had it all nicely filleted, nice chamfers everywhere, it was all beautiful. But ultimately, I think I was just kind of procrastinating because, I mean, you can see I ended up not going with that at all anyway, but I've been trying to be more focused on the more important things. So after I spent that time indulging, trying to stuff around with the O-Drive Micro, I realized, okay, no, that's not key importance right now. Key thing right now is let's figure out the base. That needs to be done, and I've got a reasonably good idea of how that will work. And then now I think the next major thing is how to actually fix the base to this outer ring so that they are stuck together. I think that's a pretty big one. And just I might just like pick some arbitrary size of box, and if what I need to put in there doesn't fit, then I'll just make the box a bit bigger. Deal with it. Deal with that problem when it comes. But I've got like a kind of like hierarchy in my mind of like how important these problems are. Like one fairly low on the hierarchy is like changing the way that these cables route in here. Because right now I have, well, this is kind of hard to see, but I'm intending on the cables coming through like this channel here and this one for the motor cables. But I am not super happy with this big cavity showing here. And I want to change that a little bit. I also need to change how the cables are coming up from the base to come up through here. There's obviously something in the way right now. So I've got like a hierarchy in my mind of like how important each of these things are. And yeah, I'm just trying to like work through them in order of importance, approximately. But it is tricky with some aspects of this, like this depends on this, which depends on this, which depends on this, which depends on this. And it's like, what do you do? And I think the answer is you just got to pick somewhere to start and then revise it as you go. Yeah, that seems to be working all right for me. But it feels like it's not as fast as it could be. But, you know, speed is not the name of the game. Anyway, so my electronics binder is coming along. It's quite nice. I don't know if I love the binder itself, but it works. I've got my resistors, and these are all in their nice little pockets. These sleeves worked out fairly nicely. They are a little bit fiddly to get things in and out of, but they've got this nice flap on the top, which hopefully means that if the whole thing turns upside down, nothing comes out, which is comforting. Yeah, I've got my resistors, I've got capacitors, but you can see that right now nothing is actually labeled. So like if I'm looking through my capacitors, it's just like I just have to like read the text on each one. And the reason for that is because I'm not really sure exactly how I want to have some kind of like a sheet that goes like a backing sheet that goes behind each one so that it kind of tells me like the key information, but I'm just not exactly sure what information I exactly want for each of the components to then get it printed out. Got my LEDs. It's really good. I like it. One thing that I didn't really anticipate being a problem is that I'm filling all of the rows out like this, where I've got like, this is the first cell to be filled, then this one, then this one, then this one, and so on, which means that for most of the components, like if I'm not filling all of them, I'm filling the top ones first, and then if I've got more, I fill the next one down, and then if I've got even more, I fill the third one down. But what this means is that the top row of every single one of these pages is filled with something. The middle row is like half filled sometimes, and the bottom row is only filled sometimes, which means that when this whole thing is put together, it's like very top heavy, if that makes sense. Like the top does not compress nearly as tightly as the bottom does, which isn't really a concern for now. Like the binder still holds them all, but yeah, was not really expecting that. And I also don't have any integrated circuits in here yet. I do have some integrated circuits right now, but I'm still storing those just in like in the orange box that you can see there. And that works, but I might move them into here later, but I need to figure out some way to not break them when they get compressed. But yeah, so it's coming along. It's getting there. Yeah. All right. Cool. I'm pretty sure it's everything. I'm just looking around. I had my desk of things here to demonstrate throughout the stream, but I'm pretty sure I've addressed them all. Oh, actually, no, there's one more thing. I can't believe I forgot. Okay, the last thing is to do with going back to using the spring to do the throwing instead of the hand. And yeah, so a big question here is like, I have some springs. I've got like a kit of springs already available. And I was wondering with like how strong, what like spring stiffness would I need for the spring, and how far would I need to extend it by in order to throw the ball to different heights? Because if I need either an impossibly stiff spring, or if I need to extend it ludicrously far, then this idea is not going to work, and it's just not going to fit. So I did a bit of calculating to figure out the relationship basically between like throw height, the stroke that we can throw over, and like throw angle and various other things. And after a little bit of stuffing around, it's been a little while since I've done this. I finally got there, and I did it 2 ways and got the same answer both ways, so I feel pretty good that this is right. But it's such a weird equation. Look at this equation. So we've got 2 copies of it, one down here and one down here. And I'll show my whole working out so you can pause and follow along if you're interested. I will warn though that while I was doing this, I forgot the commonly used symbols for these things. So I have KE is elastic potential energy, KP is gravitational potential because P is potential. I don't know. I was just doing whatever felt right. And KV is velocity kinetic energy. Yeah, I forgot my symbols, but the gist is correct. But the end is that look at this equation. We've got a cos and then a 1 over cos squared. What the fuck is that? But I'm pretty sure it's right. And I got ChatGPT, or actually Claude this time through GitHub, to write me some code to plot this. And I can show you the result. It's still a little bit janky, but the end result is that we can set some angle of the throw, we can set our spring constant, and we can set what the target height is. So if we want to throw to, let's say, 1 meter high, and we want the angle to be 10 degrees, I need to check this to make sure that all of the calculations are correct, but it seems qualitatively correct. We can see that with a spring constant of 100 100 newtons per meter, we would have to stretch the spring by 20 centimeters, that's too much. That's too far. We don't have that much length in the first place, so we need to have a stiffer spring. So we can change this and then see how the stiffness of the spring affects how much we need to stretch it by, and then also like how high do we want to throw, and then how much do we need to extend the spring. And an interesting thing here, so like let's say that the maximum height that we'll ever throw at is 2 meters. So let's go to 2 meters. And let's say that we are allowing for 150 millimeters of stretch. So let's go to there. So we need a spring that has a constant of 450 newtons per meter. And of course, the spring kit that I have is kind of, they're definitely not rated, but I can like test them all empirically to get something pretty close to this. And yeah, so we can see how does our amount of stretch change as we throw higher or lower. So right now we're throwing 2 meters and we're stretching by 150 millimeters. If we're only throwing by 1 meter, we still need to stretch by 106 millimeters. So it's very non-linear. Yeah, which I don't know. This is like the last 12 hours I've gotten this working, and I'm still just kind of playing around with it and like trying to get a feel for it. But I've found this to be a very useful way to kind of vibe how this sort of system would behave, and like what we would need to get out of the system in order to how the system would need to work in order to get what we want out. Yeah, so this kind of simulation has been very useful. I've been enjoying it a lot. It's been good, and I'm glad that my calculations worked out. I had some weird trig identities in there that it's been a while since I've used. Frisco says, guessing $sign like spreadsheet refs. For Onshape, I don't think Onshape uses the $sign at all. But we can give it a go. Let's see what happens. Let's do the name. No, it still just comes in as $outer diameter. Yeah, they've got a really, really weird syntax for certain things. Like if you want to do you can have like if statements in your queries. So like if you wanted to, you could have like, if outer diameter is more than double inner diameter, then the thickness is 2 millimeters or something. Oh, this is what you're saying you got to work. Oh, nice. Good work, Alice. I am very keen for that. There's quite a few places where I would use this, and yeah, I'm very keen to see what you did. Very nice. All right, head to Zulip and check out Alice's approach if you're curious. I'll put a thing a link in this video in somewhere below, so you can more easily find that if you're watching this in the future. Yep. All right, cool. That's it. That's enough rambling. Yep. There should be a stream next week, hopefully. Hopefully I will have enough time to do Jogglebot stuff next week. And yeah, I'm very torn about whether to make more prototypes of this stuff, because this prototype was very useful to learn about how the system would behave, but I don't really want to just be like printing heaps and heaps of parts and having to like scrap them, especially because these parts are quite large, most of them. I'm in two minds about making prototypes, but maybe by next week I'll feel solid enough about some aspects of the design. I really want to get the hand throwing part to like mount onto here. I would love to get it to like pitch, throw. That'd be so good. But I don't think that ODrive micros will be here before next week, so I might postpone that for a bit. But yeah, all right, cool. I hope you found that interesting. And yes, lots of opportunities for good feedback if you are so inclined. Lots of big questions as to whether I'm going to break my Jetson, and hopefully not. Yeah, we'll see. All right. I will hopefully see you next week. And until then, have a good one. And good luck with everything you're doing.